Welcome to the Using FPGAs with the Intel oneAPI Toolkits online training. My name is Ogene Uriri. This is the first of a two-part introductory course on using oneAPI with Intel FPGAs. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the email address provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. The objectives of this online training is to get you familiar with the Intel oneAPI product, the data parallel C++ DPC language, which enables the oneAPI product, and the oneAPI toolkits for FPGA. This training also aims to teach you the development flow for FPGAs when designing with the Intel oneAPI toolkits. This online training will cover an introduction to the Intel oneAPI product, DPC language, FPGAs, and the development flow for using FPGAs with the Intel oneAPI toolkits. Let's now get started with the introduction to the Intel oneAPI product. To fully appreciate the Intel oneAPI product, we first take on the concept of heterogeneous computing. Heterogeneous computing refers to a single system having multiple architectures. It has become a fast-growing trend for achieving optimum performance in diverse workloads. The individual strengths of these architectures, such as spatial, vector, scalar, can be combined for the benefit of the overall system. These strengths, which range from performance, throughput, latency, I/O flexibility, memory bandwidth, can be combined. The advent of heterogeneous computing gives developers the ability to optimize specialized inline and offload workloads to meet various business needs. Workload diversity continues to plummet, with more and more demand for hardware that can handle the diversity. However, no single architecture is best for every workload. Hence, the workload diversity is driving the hardware diversity. Therefore, it is safe to conclude that the future is a diverse mix of scalar, vector, matrix, and spatial architectures deployed in CPUs, GPUs, AI, FPGAs, and other novel accelerators. The growing trend of heterogeneous computing is not without its challenges. This is because you are dealing with multiple architectures limited by programming barrier. Today, you find that each architecture requires separate programming models and toolchains. The toolchains will typically need training and licensing to use them. You end up needing to have license and training for various compilers, IDE, debugger, analytics or monitoring tool, deployment tool, and many others for every architecture on the system. The challenges doesn't stop with licenses, but extends to even debug, monitoring, and maintenance of your cross-architectural source code. Some of these toolchains can also pose difficulty in integration across proprietary IPs and architectures. Plus, there is no code reuse. You prepare code per architecture you are targeting. These challenges also extend into the overall software experience, leading to software development complexity, which limits freedom of architectural choice. Thus, with heterogeneous computing comes this huge barrier to entry that makes it unappealing despite its numerous advantages. Only those with the resources to make isolated investments required for technical expertise can afford to take advantage of diverse architectures on single system. To address the programming challenges posed by multiple architectures, a unified programming model was developed called the oneAPI. oneAPI delivers a one-shoe-fits-all model to simplify development across diverse architectures. enabling users to take advantage of diverse architectures easily. This product provides a common developer experience across scalar, vector, matrix, and spatial architectures, which is deployed in CPUs, GPUs, AI, and FPGA devices respectively. It also guarantees an uncompromised native high-level language performance with industry standardization and open specifications. The Intel oneAPI product was developed with future developers in mind, providing a model that supports diverse workload efficiently. The advantages of this product is far too numerous. It goes without saying that you have one set of toolchain, libraries, language, and compatibility tool to handle all of your application workloads requiring diverse architectures. Developers can now have faster turnaround time as development complexity is drastically reduced using the inbuilt tools. For instance, you can iterate and complete proof of concept designs quicker through emulation and reports by performing functional verification and performance tuning respectively, before having to perform a long hardware compilation, which typically takes several hours for FPGAs. You can get runtime data across your host and accelerators through the vTune profiler, plus easily develop complex hardware patterns implemented through macros, pragmas, headers, and other built-in language features. Using oneAPI model provides you an extensible code that is compatible with existing high-performance languages, such that you can now reuse source code across multiple hardware architectures and vendor platforms, although code will need optimization to be performant on a different architecture. Furthermore, the problem of barrier to entry is reduced with the commonality of sequential programming languages and IDE integration that you can leverage. This, of course, improves ramp-up and debug time for developers. Now that we have understood what the oneAPI product is, let's take a look at what makes up the product and what is essential for FPGAs, the accelerator this training is meant for. The Intel oneAPI product consists of Data Parallel C++, DPC++, which enables direct programming, a bunch of libraries that supports API-based programming, and of course, analysis and debug tools. DPC++, which is the programming language for oneAPI, is SYCL, maintained by Kernels and some community extensions. All of the source code you will develop for your design will be written in DPC++, a combination of modern C++, version 11 or higher, and SYCL 1.2.1 and higher. We will look at DPC++ in the next section. The oneAPI product also includes a DPC++ C++ compiler built on a CLang LLVM front end for RTL generation and a DPC++ runtime for resource allocation and management during execution. The oneAPI toolkit for FPGAs includes support for direct programming with DPC++, with the addition of analysis and debug tools. The general idea is to pair the value and flexibility of an FPGA with that of the oneAPI programming model. FPGAs are great for data-dependent parallelism workloads where spatial architecture and pipelining is the key differentiator from other architectures. FPGAs have programmable low-latency IOs for accelerator-to-accelerator and accelerator-to-host communication. FPGAs have flexible on-chip memory architecture that allows developers to create multiple banks for parallel read, writes, or to move large amounts of data using a high bandwidth memory-enabled board. By simply using oneAPI to target FPGAs as accelerator, we can take advantage of the strengths of FPGAs in targeting workloads and get efficient performance. For you to begin using the Intel oneAPI product with FPGAs, you will require the Intel oneAPI based toolkit and the Intel FPGA add-on for oneAPI based toolkit, which is now a separate download of the Intel Quartus Prime design software and the board support package BSP for the FPGA board or platform you are targeting as an accelerator. We will learn more about this in subsequent sections. Now that we have been introduced to oneAPI, we will take on the next session where we will take a look at DPC++, the language that enables oneAPI, and get familiar with the fundamentals of programming in this language. Recall we mentioned that DPC++ is a combination of C++ version 12 and higher and SYCL version 1.2.1 and higher. SYCL is based on OpenCL. Now think of DPC++ as SYCL with some extensions. If you are familiar with OpenCL, you will find that there are some similarities with DPC++. A major difference, however, is that DPC++ allows for single source targeting of accelerators. Basically, you don't require multiple files when targeting accelerators such as GPU, FPGAs, etc. DPC++ is an industry standard with open specification. With DPC++, you have a common language that targets all XPUs, albeit some tuning is required depending on the architecture you are targeting. Driving the goal of oneAPI, DPC++ provides the language that incorporates everything needed to get the best performance out of every architecture. DPC++ has three scopes, with which the compiler identifies what operation is being handed off to what device. As the developer of the program, it is important to be aware of these scopes so as to ensure you are getting the right functionality. The first scope is the application scope, which is your normal host code. Everything you can do in C++ can be done in the application scope. The host code runs on the CPU, which is typically the host for your design. As we can see in the example, declaring function pointers, setting up buffers, selecting devices are in the application scope. The second scope is the command group scope that kicks off when you submit something to the queue. The queue is the line of communication between the host and the acceleration device. We will discuss queue class shortly. This scope signals to the compiler that operation will soon be handed off to the acceleration device for execution. All the capabilities of C++ are supported in the command scope. The final scope is the kernel scope, which is kicked off within the command group scope. This scope is kicked off using the kernel dispatch command. In this example, we have a kernel dispatch command single task sent to an FPGA accelerator previously selected. Note that not all C++ capabilities are supported in the kernel scope. For instance, recursive code cannot be executed on the kernel. For a comprehensive list of the restrictions with C++, do well to check out the SYCL specification. The runtime is the program that is running in the background when you execute your model. It gets installed in the background along with other tools that you will need for setting up your system to run oneAPI. The runtime controls the execution and data passing to the heterogeneous device. It also handles the kernel and host execution in the order that is imposed by the data dependency. Runtime takes care of passing data back and forth between the host and device. It makes queries to the device, and so on. Think of the runtime as the layer your code interacts with. A note about Lambda functions. Lambda functions are unnamed functions and are quite common to C++ users. You will come across them in most of the example codes in this training and in our DevCloud tutorials. We use them to keep the code all in line without having to wrap it into a function. Thus, it takes the place of what will be a function pointer, keeping our samples short and simple. Two common constructs in DPC++ that require function pointers as arguments are queue submissions and kernel dispatch functions. When writing these constructs, you will find that Lambda functions are utilized instead of the function pointers. To get you familiar with them, a simple guide is presented in the code snippet as shown. The square bracket tells what you intend to capture from the function. We usually use an equal sign or an ampersand sign. The equal sign implies that you want to capture everything, but you want it passed by value. The ampersand means you capture everything, but you will be passing it by reference. In the kernel dispatch call, we use the equal sign when using the Lambda function because we are physically passing data back and forth to the device by value. Next is the regular parenthesis, which represents the parameters we are passing into the function. Objects like handler are captured in the parenthesis when we need access to the member functions of that object. For instance, the kernel dispatch is the member of the handler class, and we will make a lot of calls to it. So we do not just pass the handler, but we give it a short name to avoid writing handler out in full all the time. Lastly, we open a curly braces where we put the normal statements for functionality like in any C++ function. On a final note, Lambda functions are not compulsory. Feel free to wrap everything in normal functions and point to those in your own code. In the next couple of slides, we will look at some of the DPC++ class to enable us get an idea of how to write a DPC++ program. The device class represents the accelerators in a oneAPI system. These accelerators can be GPU, CPU, FPGA, and any other novel architecture. The device class provides member functions that we can use to grab some information about the device available to the host. For instance, using the function getInfo, we can find the name, vendor, and version of the device. We can also get the width for built-in data types, the clock frequency of the device, the cache width, and sizes, and whether the device is online or offline. You can have as many accelerators as you so desire, as there is no limit. In this example code snippet, we show how to make a query to see the devices that are available and get information about them. DPC++ also has a device selector class. This class enables selection of a device to execute kernels on. You can select a device of choice by using the selector construct described in the code snippet. You can also use the default selector, and the default device available will be used for acceleration. We use the device selector when we create a queue, as shown in the example snippet. See how we have selected the FPGA as the device for acceleration in the code snippet using the construct ext::intel:: FPGA_selector selector. The comments in purple show how to make selection for other devices. Next, we will take a look at the queue class. Another DPC++ class is the queue class. It is the line of communication between the host and the device. It is a mechanism where work is submitted to a device. The queue submits command groups to be executed by the SQL runtime. Recall that the DPC++ command group scope is initiated with the queue.submit command. When this command is initiated, it signals to SQL runtime that groups of work is to be passed on to the accelerator for execution. You can have as many queues sent to a device. However, a queue maps to a single device. In the example code, we have declared a queue to a device with the selector and initiated the command group scope using the queue.submit command and capturing the handler class by reference using the Lambda function. The handler class contains all the command group functions of SYCL. Next, we will discuss the DPC++ kernel class. The kernel, as we mentioned previously, is all of the code that we want to send off to the accelerator device for acceleration. The kernel encapsulates the code that will be implemented on the accelerator. Although the user does not explicitly construct the kernel object, however, when a kernel dispatch function is called, the kernel is constructed. The dispatch call for kernels are the parallel for and the single task. Using any of these functions constructs the kernel. In the example code shown, the kernel dispatch call is initiated by using the single task function. Notice that the kernel scope begins right after the curly braces is opened. Thus, the simple vector addition will be handed off to the accelerator device for execution. The single task kernels are those that are constructed with the single task dispatch call. These kernels allow complex, lengthy data paths to be built from custom hardware in FPGAs. They are useful when we intend to offload code with dependencies that are difficult to execute in a data parallel fashion. Since FPGAs shine in algorithms that are in this manner, this becomes the ideal and recommended kernel for FPGAs. When you glance at single-task kernels, they typically look like CPU code containing an outer loop to process all the data. The code snippet shows an implementation of a vector addition using a for loop in CPU. The corresponding FPGA implementation as a single-task kernel looks similar. We will be seeing many more single-task kernels as we continue in the training. The counterpart to single-task kernels is the parallel kernel. Parallel kernels allow multiple instances of an operation to be executed in parallel. The kernel is constructed when the parallel_for function is called. When you think of parallel operations, GPU comes to mind, as their architecture allows for parallel execution of multiple instances. The parallel kernels, therefore, are best implemented on GPUs. Now, you can attempt to use a parallel_for kernel on an FPGA. While your operation will be functional, it will result in a less optimal implementation. The code snippet shows the same vector addition we looked at previously, implemented for CPU with the for loop. Take a look at the corresponding GPU kernel implementation using the parallel_for dispatch call for the kernel. Amongst other differences, notice that there are no outer loops as in single-task kernel for FPGA implementation. The final DPC++ class we will look at are buffers and accessors. Buffers encapsulate data in a SYCL application in both devices and host. Buffers are data abstraction that represents one or more objects of a given C++ type. While a buffer itself is a single object, the C++ type encapsulated by the buffer could be an array that contains multiple objects. Buffers represent data objects rather than specific memory addresses, so they cannot be directly accessed like regular C++ arrays. Since a buffer object might map to multiple different memory locations on several different devices or even on the same device, for performance reasons instead, we use accessor objects to read and write to buffers. Accessors are the mechanism we use to access buffer data. The runtime is informed of how we intend using the accessors we create by the type of access mode we provide the accessors. In the example code, we create buffers for vector A, B, and C, and we create accessors A, B, and C to access buffers A, B, and C in a read-only, and write-only manner, respectively. The runtime determines data dependencies with the privileges or accesses we have given to the accessor we construct. It also uses this to determine the order in which kernel will be executed. Something else to consider when writing your DPC++ program is the necessary header files required to be included. Always include at the top of your program the cl/sickle.hpp header file when writing oneAPI programs and the cl/sickle/intel/fpga_extensions header file when writing programs targeting FPGAs. To make using classes less verbose, include the sickle namespace. Now that we have run through the fundamental classes for writing a DPC++ program, we will take a look at an example that will walk us through the basic steps in creating a oneAPI program targeting an FPGA as the accelerator device. This example code is a simple walkthrough of the DPC++ program. The first step in writing your DPC++ code is to create a device selector that will target the FPGA or whatever accelerator device you have in mind. To do so, we use the construct ext:/intel:/fpga_selector, all in lowercase letters. By doing so, we have successfully set up an FPGA device selector and let the runtime know that we want to use the FPGA accelerator. In the second step, we create a device queue. This is like setting up a line of communication with the acceleration device, which is the FPGA. We will pass data and kernel dispatches through this queue. When we establish the queue, we need to also tell it what device it would interact with. Hence, we pass in the selector from the previous step. The next step is to create buffers. We will be using the buffers to encapsulate data that we will be using later on in the device. We declare it with the keyword buffer. We give it a name and tell it what data we are encapsulating. In this example, we are encapsulating the pointers A, B, and C in buff A, buff B, and buff C respectively. Since the pointers don't have a size associated with them, we use a range in the buffer declaration because the construct for buffer requires that when we use pointers, we are to provide a range. The number 1 refers to the dimensionality of the range A, while N refers to the number of items that you are encapsulating. If you use a C++ vector, you won't require a range. Now to step 4. We submit something to the queue. This will also be the beginning of our command scope. To do so, we use the queue.submit command and we begin submitting what we want into it. Notice the Lambda function notation here, signaling that we are capturing everything and passing it by reference. The curly brace holds the actual function we want to execute. With the queue submission done, the next thing will be to hand off the necessary data that the device will be needing. To do so, we create accessors that will be able to access the data encapsulated in the buffers. Right in the command scope, we create the accessors A, B, and C for buff A, buff B, and buff C respectively. We also provide permissions or access modes for how we want to interact with the data. Note that these permissions are from the device's point of view. Accessor A and B are given read-only permissions. Accessor C can be written to. You can also provide a read and write permission for an accessor. Also, we hand the handler class previously established, hence the H in the parentheses in the construct. Now that we have successfully set up the FPGA as the device of choice and set up the line of communication and also buffers and accessors, we are ready for the final step, which is to dispatch the kernel. Still in the command scope, we create our single task kernel using the single task dispatch call. Notice the Lambda function at the dispatch call. Though Lambda functions are unnamed functions, we can give it a name. This really helps when we are looking at the report. We can tell what kernel the analysis is done for when it is named. In this example, the name vector add is given to the kernel. The code inside of the curly braces, which is the kernel, becomes part of the FPGA design and will be handed off to the FPGA for execution. Note that you can have multiple kernel scopes inside your program. That about wraps up the fundamental steps required to write your DPC++ program. The contents of buff C will be copied to the pointer C when the function finishes. This is because there will be buffer destruction of buff C upon completion. We will take a look at this later. Hopefully, this example has given you a good head start to how the DPC++ program looks like and how to get started on writing one for your design. We have mentioned earlier that the runtime determines which kernel to execute when we have multiple kernels. How it does this is by looking at how you are using the data you're accessing. In this example, we have multiple kernel scopes, and they can all run at the same time. However, the runtime will first take a look at what permissions have been granted to the accessors, and with that information automatically determine execution ordering. Thus, if a kernel needs data that another kernel is producing, it will place an order dependency on that kernel. The example here shows kernel 1 is accessing buffer A, and it is doing so in a read and write manner, implying that kernel 1 is reading from A and also writing to A. This is represented in the graph. Kernel 2 is also accessing buffer A in a read and write manner. The runtime figures out that there is a dependency here. It has to wait on kernel 1 to finish writing into buffer A before kernel 2 can begin reading from buffer A. Looking at the execution graph, you find kernel 2 dependency is shown. Kernel 3 is accessing buffer B in a read and write manner. There is no need to wait on kernel 1 and 2, and hence the runtime knows to execute kernel 3 in conjunction with kernel 1 and kernel 2 at the same time. This is also indicated in the execution graph. Kernel 4 is going to be reading from buffer A and writing from buffer B. This means it must wait on A and B to get finished before the runtime kicks off executing this graph. In the execution graph, you can see that kernel 4 is waiting on kernel 2 and kernel 3. Its execution is the last before the program completion. The application scope, which is the host code, executes asynchronously to what is being executed on the accelerator device. Looking at the order in which the scopes are arranged, you typically go from application scope to command scope and then to kick off the kernel. However, when the kernel is dispatched and begin execution on the accelerator, whatever host code is after the kernel code continues running. If you need the host to stop and wait for the computations on the kernel to finish first before continuing to the host code, then you must impose the synchronization yourself. We will look at two ways you can impose this synchronization. The first way to impose synchronization is by placing an accessor in the application scope. So far, we have only used accessors in the command scope, which is from the accelerator device's point of view. Accessors created in the application scope are for the host. When the host accessor also points to the buffer the kernel is accessing, runtime creates a dependency node in the execution graph, in essence, blocking execution at the host until the data is ready. This example here shows an accessor in the application scope, and since the accessor is pointing to the same buffer that the kernel is accessing, the host has to wait until the kernel completes execution in order to access that buffer, thus imposing synchronization. The second way to impose synchronization is by declaring the buffers in their own scope, that is, creating buffers within a separate function. When execution advances beyond this function scope, buffer destructor is invoked. This causes data ownership to be relinquished and the data is copied back to the host memory. In this example, the buffer declaration and the queue submission has been put in its own function, void DPCPP code. The buffer declared in the kernel is within the function, meaning that before coming out of the function, the buffer has to be destructed. This happens because of the rules of C++. This has now placed the host on a hold for the kernel to complete execution. This form of synchronization can also be achieved by simply using curly braces around the buffer. although this isn't as friendly as it makes the code difficult to read later on. There is still so much to DPC++. We have barely scratched the surface. To learn more about this language, you can download the DPC++ book in PDF or EPUB for free on Springer using the link provided. Also, there are lots of training modules available on our Dev Cloud that you can use to practice and learn. By signing up for free on our Intel Dev Cloud, you can have access to these tutorials. Next, we will dive into FPGAs, what they are, and why you should be interested in programming them. If you are unfamiliar with FPGA, this will provide you a simple introduction. FPGA stands for Field Programmable Gate Array. Gate array being an old concept. The gate refers to the transistors, which are the tiny pieces of hardware on a chip that make up the design. Array means there are a lot of them on the chip, as many as billions of transistors. We don't program at that finer granularity. Rather, we group them into larger structures. Field programmable means that all the connections between these internal components or structures, such as lookup tables, clocks, and memories, are programmable in the field after deployment. Simply put, FPGAs are programmable hardware. How does an FPGA become what you want it to be? Remember, FPGA has billions of transistors. This image shows a simplified representation of the blocks inside the FPGA. These are building blocks of logic and other functions. The software where your compiler is running will choose the building blocks inside of the FPGA for your design. By choosing, it also determines what type of block and what placement is suitable for it. Remember, there are millions of these blocks, so choosing which one to build with takes a while. Next, you configure the building blocks to what you need to load into the lookup tables. Finally, you connect these building blocks. This process, which involves routing, also takes a while. These custom choices eventually determines the FPGA's functionality. Next, we will look at what these blocks inside the FPGA are. The blocks that are inside of the FPGAs are lookup tables and registers, and they usually occur within the same block. The lookup tables make up your logic functionality. The register aids with synchronizing your design, as your design will go through a register with the clock. The FPGA also have memory blocks. These on-chip RAM blocks are 20 kilobytes natively. We can use them at 20 kilobytes at a time or put them together to form larger memories that can either be deeper or wider, hence customizable to suit your design needs. The DSP blocks, digital signal processing blocks, are another kind of blocks that are available on the FPGA. They typically have a multiplier and an adder in addition to the registers and mux. They are single precision floating point for the FPGAs that you will use in working with oneAPI. Almost all the math functionality that you will code up will use the DSP blocks or several DSP blocks. When the blocks required for your design have been built up, custom routing is performed to connect the blocks together. This routing physically takes most of the space of the FPGA. It requires lots of muxing to connect one block to the other. To get started with oneAPI on an FPGA, these are the tools you need. The Intel oneAPI base toolkit is what you install first. With just the base toolkit, you can develop and optimize an FPGA workload. That is, you can perform emulation and compilation to an early image and obtain an optimization report. With just this tool, you can get a lot of practice on how oneAPI and FPGAs work. The oneAPI output is a performance-accurate FPGA hardware model of the algorithm. Accelerate your workload by using the Intel Quartus Prime Pro Edition software to link the oneAPI FPGA hardware model to the supported FPGA platform. Intel Quartus Prime Pro Edition software is an add-on to the Intel oneAPI base toolkit and compiles the FPGA hardware models generated by oneAPI with those in the FPGA platform to program the FPGA. Intel Quartus Prime Pro Edition software is not required to develop accurate FPGA hardware models using oneAPI, but it is required to compile and run on the FPGA platform. You typically won't be working with a standalone FPGA when using oneAPI. The model comes as a hosted model, meaning you have a card with an FPGA in it. There is also the DDR embedded, which we will refer to as global memory. A PCIe interface and other IPs are in the card. Besides what you've coded as kernel for the FPGA performs other functionality like communicating with the DDR and so on. This portion of the design is pre-built and not dependent on your source code. The Intel FPGA cards currently available to use with oneAPI are distributed through third-party companies showing on your screen. You can get the FPGA boards from High-Tech Systems, Bitware, and Terasic. Use the links showing on your screen to learn more about how to get them. You can also get updated information on supported boards for oneAPI based toolkits on the Intel FPGA add-on webpage. After all said and done, why should you care about programming for an FPGA? Eventually, it comes down to what the FPGA can do better than others. Those algorithms where the advantages of using a custom hardware gives better and faster performance. FPGAs perform well on algorithms that have many carry loop dependencies. This type of algorithms will run well on the FPGA, even beating the CPU performance. Another kind of algorithm that FPGAs are good at are those that take advantage of the customized memory structure that is built. For example, compression has a lot of carry loop dependencies because of the large data that comes in. In compression, you are looking to compare new data to current data, requiring a sort of looping through more and more values as you continue comparing it to lots of different data. As many values as you can grab from the memory at one time, you can do comparison for. Hence, taking advantage of the memory structure of FPGAs, you can achieve this in a good time. This type of algorithm is difficult to express in parallel type program, hence GPUs will find it difficult to execute. Genomic sequencing is similar to compression. It also involves comparing present and past values in large volumes, and the FPGA performs these algorithms really well. Key value store is basically hashing, and it is used for database. You find such algorithms in bitcoins. It takes advantage of the memory structure of FPGAs. Thus, you are able to pull a lot of values out at a time and compare against a set of another values all at once in very few clock cycles. Database analytics is also similar to key value store. You find that all of these algorithms take advantage of the custom memory structure FPGAs can build for you. An example design that comes along with your installation of oneAPI based toolkit for FPGA is the Gzip Compression. The design performs compression. It has 3 different kernel scopes: CRC, LZ77, and Huffman. It also takes advantage of the kernel to kernel pipe architecture such that kernels can communicate with each other easily. Our FPGAs can build the pipe hardware, thus creating a seamless connection between the kernels. You are highly encouraged to try out this design for yourself and understand why it has a great performance. Next, we will take a look at the development flow for using FPGAs with the Intel oneAPI toolkit. This is the mechanics involved in using oneAPI with FPGAs, and it is very important to stick to this flow. Again, to get started, you need the Intel oneAPI based toolkit, which will enable you perform emulation and optimization process on your design. To deploy on the hardware, you need the FPGA add-on, which is a download of Quartus Prime Pro and the board support package, depending on the FPGA platform you are targeting. On your screen is the link to the web page to download the oneAPI toolkit. The oneAPI-based toolkit supports emulation and the optimization report generation. If you need to make compiles to the physical FPGA hardware, you should then download the Intel FPGA add-on for oneAPI-based toolkit. Be sure to comply to required versions of operating systems by checking the release notes. The version you will download will depend on the board you are targeting for acceleration. Or you can skip the entire installation and just sign up to the Intel Dev Cloud with the link provided on your screen. With your free account, you can access nodes with cards installed in the group FPGA runtime and also nodes with extra memory for full FPGA compiles in their group FPGA compile. There are also tons of tutorial examples that you can access on it that will help with practicing. It is important to follow the FPGA development flow for oneAPI projects. The chart here shows the order of executing the development flow and what amount of time each step executes. The first step in the flow after your design coding is ready is emulation. This step checks that your code is functional, devoid of syntax errors, and provides the appropriate results. It executes on a software compile, which will run on the host, and it is very quick, taking seconds to complete. Once you are satisfied with the functionality of the DPC++ code, the next step is to compile to an early image. This will generate a static report which will convey most of the bottlenecks inside of the design for which you can optimize performance. This typically takes minutes to compile to this report, in worst case 20 minutes. Your job will then be to inspect the report, analyze the bottlenecks, and try to eliminate them by recoding your design. Then you go back to the first step to perform emulation, and then to step 2 for as long as it takes to clear out the bottlenecks. When you are satisfied with the optimization from a performance standpoint, you can then proceed to perform a full compile and hardware profiling, which will generate an executable that you can run on the FPGA. These usually takes hours to complete. Not sticking to the flow and rushing off to do a full compile can potentially slow down your work and make you lose time that would have better have been spent on optimizing your design. How do we run the commands for the various steps in the development flow we have just looked at? This construct shows the anatomy of the DPC++ command targeting FPGAs. The DPC PP stands for the language Data Parallel C++. -F Intel FPGA in lowercase letters represents the target platform, which is the FPGA device. It comes right after the DPC PP keyword. Next is the input files, which can either be your source files in .cpp format or object files in .o format, after which you provide link options and some FPGA specific arguments. We will go over some of them in the next couple of slides. The commands required are all in the oneAPI programming guide. Emulation is the first step in the development flow. The goal of this process is to answer the question, does my code give me the correct answers? Thus, in this step, developers can verify functionality of design through CPU compile and emulation, identify quickly syntax and pointer implementation errors for iterative design and algorithm development, enable deep system-wide debug with Intel distribution for GDB, and functional debug of SQL code with FPGA extensions. Emulation takes seconds to complete compilation. It quickly generates code that runs on the x86 host to emulate the FPGA. The command you will use for emulation is showing on your screen. dpcpp-f Intel FPGA, your source file .cpp, all in lowercase letters. Then -dfpga_emulator in uppercase letters. Your source file may be more than one, depending on how you have structured your code. -d is defining that the FPGA emulator selector device is to be used for this compilation. Inside of your code, you will need to have this construct shown in the code snippet. It is necessary as it helps the compiler determine that emulation operation should be performed rather than a full compile. Wrap your device selector declaration in the if-def-else statement. Upon completion of the compile, an executable file will be generated. This executable runs on the host, thus you won't need an FPGA card to execute it. Report generation takes minutes of compilation. The report shows the bottlenecks and also provide hints on how to optimize optimize for those bottlenecks. With the report, you can identify any memory, performance, data flow bottlenecks inside of your design. The report also provides you with useful suggestions for optimization techniques that will resolve the bottlenecks it has identified. It generates area and timing estimates of your design for the FPGA that you are targeting. The command to generate an optimization report is showing on your screen. The -f-sickle-link defaults to early image. Thus, the compilation will stop at an early image. Along with that early image, it generates the report. The early image is an XML file that shows or represents the blocks and what pieces of IP of the FPGA are connected to each other and put together for your design. All of this is produced within minutes. The -XS hardware is a switch which will always be included whenever we are not targeting the emulator device. The reports will be in a reports folder of your file project directory that is generated after the compilation is completed. It is a .html file which you can open up in a browser. Finally, the Bitstream compilation, which is performed when we are absolutely certain that our design is optimized from a performance standpoint. It typically runs for hours. This compilation runs Intel Quartus Prime software under the hood. You do not need a license for the Quartus Prime software. When the compilation is completed, you will have an executable that you can run on the FPGA. At this point, you'll be able to run an accelerated program. You do not have to worry about timing closure, as this is automated for you. The eventual clock frequency will be reported back, showing you what the achieved clock rate for the FPGA was. Also, there is no need to perform verification from a simulation standpoint, since pre-tested IPs are what is put together for the FPGA. However, you may want to ensure that you are getting the exact results achieved at emulation. If you have used some pragmas or attributes that you asked the emulator to ignore, you will need to enable them at this stage of the development, and this can potentially affect your results. You can use the VTune profiler, which will provide some additional reports that you can use for performance analysis and fine-tuning if need be. The command for performing full compilation is showing on your screen. You can take out the excess profile if you just want to compile to FPGA executable without profiling the hardware. When you include the -XS profiler in the compilation command, the profiler will be instrumented within the image and you will be able to examine data with the Intel VTune profiler when running the executable. Be aware that this will potentially slow down further the compilation time, and it also takes up part of the hardware and reduces the frequency. What if only the host code changes in your design and you have to do a full compile again? We can use the reuse flag indicated by the -reuse-exe. This will let the compiler know that you want to reuse the FPGA bitstream previously generated and that there are no changes in your kernel scope. With this approach, your full bitstream compilation, which will typically take hours to complete, will now take minutes. We have successfully learnt the steps in the development flow and how to execute them. This has brought us to the end of this first part of the training using oneAPI with Intel FPGAs. We have come to the end of the training using Intel FPGAs with the Intel oneAPI Toolkits. To summarize, we take a brief recap on what we have learned in this training. The Intel oneAPI product addresses the challenge of diverse architectures requiring diverse toolsets and languages by providing a unified language for multiple architecture. DPC++ is the oneAPI language, and you should think of it as SQL with some extensions. FPGAs provide a custom approach towards building designs, and as such, combining with oneAPI can provide a powerful accelerator for algorithms. To perform acceleration on the FPGA, the development flow begins with emulation, followed by optimization report generation, and finally a full compilation when you are satisfied with the optimization of your kernel. The follow-on training will look at some optimization techniques that makes oneAPI a great product to work with for FPGAs. You are highly encouraged to take the Introduction to Optimizing FPGAs with the Intel oneAPI Toolkits online training to become acquainted with these methods. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email ogeneurioderoko@intel.com with any of your thoughts or comments on the Using oneAPI with Intel FPGAs Part 1 online training you have just received. This concludes the training. Again, my name is Ogene Uriri. Thank you and have a good day.